what we have in Rust is pretty similar. So we don't have only pointers, but we have own boxes. An own box with this tilde is a reference that's responsible for owning that storage. It owns the box, it owns the storage that it's referencing. Rust has managed boxes as well, and it's actually in 0.9 still supports the @ symbol to give you a managed box, which is automatically garbage collected. That's actually going to be removed by 1.0, or it's expected to be removed. That you should be able to implement any kind of managed storage that you want in Rust as a library instead of anything built into the language. So there are both garbage collected and reference counted ways of doing storage that are part of the Rust library, but there's no reason you can't implement those yourself, starting with the explicitly owned boxes. So let's look at what that means. So when we have an own pointer, if we use it in an assignment, we're moving ownership to the new reference. Here we started with an own pointer, so I'm using static strings. Normally if you're using static strings, you wouldn't actually need to make own strings, but this makes the examples easy, and if you were modifying the strings, then you would want to have own strings like this. So we have an own string, and then we're doing this new let, and we're assigning to stolen the value of owned. So is this code okay? This declaration? So this is actually okay, right? So this I didn't explicitly give the type here. So the type of this would be a tilde string. The Rust compiler will infer that type, and the tilde before the string literal is necessary to make an owned string. So that's a new object that's being created that has that string. So this is actually okay. And it's okay because we're doing the transfer and then we're using stolen. So what if we instead did this? So I'm changing it to, instead of using stolen here, suppose we use owned here instead. Is that okay now? Okay, yeah. So this is actually not going to be okay. This is why I sense from some of your comments on problems that people are still finding it quite frustrating to program in Rust, and that's understandable. It is very different from what you've done in other languages, and it's a fairly big hurdle to get over that now you're using a language where things that used to seem perfectly okay, doing assignments and using variables, now lead to compiler errors. They're necessary to provide this memory model, and the rule that happened here, once we moved owned to stolen, now we can't use owned anymore. So what we'll get from this code is an error from the compiler saying that we're using a value that's been moved. The wording is a little bit awkward, but there's lots of notes that can sometimes be intimidating because they're so long, but give you a lot more details about why the compiler is not allowing that code. So it's not allowing it because we had this assignment here where we had an only pointer and it was moved by the let. And so what's happening in the let is we're moving that pointer to the new reference. And this error is actually pretty helpful. It suggests one way to override this would be add to ref. If we do that, what this really means once we've added the ref, so the only change now, we added the ref here, and because it's a ref, we need the star. This is sort of like what star means in C. We're following a pointer to get to its value. In this case, because we have ref, now we need the star. What the let ref is short for is actually having this borrow here. So having the ampersand, which means now instead of stealing, or instead of transferring ownership of the object and stealing it for the new reference, we're borrowing a reference to it. So now own can still use it. Both of these are okay. What about this? So now I've got almost the same code. I've changed it just by adding this scope around things. Is that still okay? It's got a red background, so that means it's not okay. Why is it not okay? Yes. Okay, good. Why is it a problem that it's going out of scope, or that what's going out of scope? Right, so when we borrow things, we borrow them for a limited amount of time. You can think of this sort of like borrowing objects in the real world. If the thing that you're borrowing had a lifetime that's limited, you can't borrow it beyond the end of that lifetime. The problem with this code is this object, right? This is a known pointer. It's created within the scope. When we're done with this scope, that object that was created here, that's done. We're done with that. Its lifetime is over. It could be reclaimed. It's not necessarily reclaimed right away, but it's, in terms of the rules of language, that object is no longer alive. We can't use it. The problem is now we've added this reference to it, like stolen's outside that, and we're trying to assign within this scope. Stolen is borrowing this object, but stolen is still alive after the object that it borrowed is no longer alive. So that's going to lead to a compiler error. So it's also I think, fairly understandable how it's worded. Kiet, who took this course last semester, is working on a project to improve these compiler warnings, because some of them are actually really incomprehensible. We'll see a more incomprehensible example later. He's written up some posts to explain how the Rust compiler actually figures out when lifetimes are violated, which in this example seems fairly straightforward. It can get quite complicated. But in this case, the lifetime of the mine object is within this scope, but the lifetime of the stolen is outside it. So we have a problem. That's the rule for the borrow lifetimes, that we can't allow an object that we borrow to have a lifetime that extends beyond the length of the loan. The length of the loan can't extend beyond the lifetime of the object that we're borrowing. It has to be contained within it. Let's try to write a procedure that's going to take two strings. It's going to take two strings as input, and what we want to return is whichever string is bigger. So how do we like this code? Do you think this is okay? I'll have a trick sometime where I have code that's correct with a red background. But even if we got rid of the println, there'd still be something wrong with it. Yeah, so what's wrong with it without the println? The compiler is going to complain before I get to the println? Yeah. Are we trying to borrow? Okay, I think you're on the right track. So when we borrow things, we have to borrow them for some limited amount of time. The time that we're borrowing it is defined by the lifetime of that variable. In code like this, what are the lifetimes that we're borrowing things for? How long are we borrowing what's passed in as S1? Do we know what the lifetime of the borrow for that variable is? Okay, so it could be the lifetime of that function. It could be that we pass in something that has a borrow lifetime longer than that. It's at least the lifetime of that function. These borrows seem to be defined by the function. They're parameters of the function. We're borrowing that object for the lifetime of the function that's using it. What about this one? How long are we borrowing the return value? And we know that that has to be a borrow. Right? We can't have some other type on that because we're returning these objects that we borrowed. Right? We're not making a copy. We're not creating a new object. We're returning one of these same objects. So what's the lifetime of the result? Do we know that when we look at the code for bigger? Do we know what the lifetime of the result is? Yeah, we don't know. There's no way just looking at this code to know what the lifetime of the result is. Right? That's up to the caller. How the caller is going to use it tells us what that lifetime is. What the compiler is trying to do is infer the correct lifetime. And what's going to happen for code like this is it can't do it. It can't figure out any lifetime that makes sense for knowing these inputs in output like that. Whether it should be able to infer that or not depends on a lot of things. So you could argue that maybe what we should be trying to do is get the Rust compiler to change to infer lifetimes like this. What we need to do instead is add annotations that give more information about these lifetimes and make that part of the type of this function. So the way to do that is add lifetime parameters. What we've added is a lifetime parameter. So the tick just introduces a new variable. This could be any name. Convention usually uses a, but it can be any name that you want. We've introduced, as part of these borrows, now they have this parameter, and so does the result. What that means when we have a lifetime parameter, so it's used on the inputs, the lifetime that Rust is going to infer for the meaning of this value is the minimum lifetime of all uses of that parameter. So we used the a parameter twice in parameters. That means the meaning of the lifetime a in this type is the minimum lifetime that's passed in of those two parameters. That means the lifetime of the result is that same lifetime. So does this make sense? Yes. Can we have more than one lifetime? Yeah, so we could have multiple variables here. We could have, let's say, 2 lifetime parameters, and we could have 2 different lifetimes on the inputs. That would be perfectly okay. What should the return type be if we did that? In this case, we'd have a problem. Right? We don't know which one to use for the return type. There certainly are functions you could write in Rust where it makes sense to have multiple lifetimes on the inputs and have different lifetimes for different inputs. Maybe you're putting those in some data structure where different parts have different lifetimes. In this case, since we need to know the lifetime of the result, and we don't know which value is being returned, the Rust rule of inferring the minimum is exactly what we want for this. This is what we've done here. Now this is the test to see if everything makes sense. Is it all okay now? Is this my trick? Using a red box when the code's correct, or is there still something wrong with this code? So what are the lifetimes that get passed in? So we're calling bigger. What is the meaning of the lifetime A going to be? Oh, do I need to initialize R here? It's a good question. So this is perfectly okay, right? I'm declaring R. As long as the Rust compiler can confirm that I never use it before initializing it, there's no need to initialize a variable when we declare it. In this case, since it's very simple straight line code, this is perfectly okay. Usually you want to initialize variables when you introduce them. But there are cases where you might have two branches of an if and you want to assign it on both branches. You don't want to make it a mutable variable. You want to declare it once outside those two branches. So there are certainly cases where it's sensible to do this. This is not sensible code. This is definitely toy code to try to make a contrived example. Is there anything else wrong with this? So remember what's going to happen. We have a lifetime parameter. We're passing in S and T. So what is the lifetime of S? Yeah, so the lifetime of S is from when S is introduced to when it goes out of scope. This is the lifetime of S. What is the lifetime of T? So T is introduced here, goes out of scope here. This is the lifetime of T. What is the lifetime of A, the lifetime parameter, going to be? Good, right? So it's the minimum of those two lifetimes. So this is going to be the lifetime of A. We're assigning the result of bigger to R. What is the lifetime of R? Yeah, so R extends beyond that scope. So this is the lifetime of R. The result from bigger has this lifetime. We're assigning it to something that has that lifetime. Well, these lifetime rules for borrowing apply to assignments here as well, right? So we're assigning to an object something that has a lifetime shorter than the lifetime of that reference. So the compiler will not allow that, and it shouldn't, right? So if we use R here, R should not be valid to use here, but it's within scope. So we need to have lifetime rules that disallow that. And that's what we'll get from the compiler. We're going to get an error that says the borrowed value does not live long enough. It does give us information about those scopes. These notes are sometimes kind of intimidating because I've dotted out the long 20 lines or so that it used to describe these scopes. One of the challenges in doing text-based errors like this is, you can't highlight the chunk of code that you want to highlight. You've got to basically print it out or give line numbers and things. So it's a little bit hard to interpret these messages. Does that make sense why it's an error? Why we can't have that result from bigger live for a lifetime beyond that scope? In this case, we could definitely make things work just by removing those brackets. Then the lifetime of T extends to the end of that scope, and the lifetime of the result will be the max of those two, the minimum of those two lifetimes, which extends to the end of the scope. Let me flash back to, so there were two errors that we talked about in my C code analysis tool. One is this one. We're complaining about not releasing the storage, not having the free there that we need. Why do we not get errors like that in the Rust code? So are we missing a free here? Do you need any frees in your Rust program? So why not? Why don't you need any frees? Are we never reclaiming storage? Yeah. Good. Yeah. So the whole point of all of this is to not explicitly need frees. The compiler is inferring where all the frees go, and because of these strict rules about how you can use references, it's possible to do that. Right. So all of the difficulty of needing to explicitly state these lifetimes and needing to worry about borrows and moves and things, all of that is to make it possible to write code that doesn't have memory leaks without needing to have frees, to make it so the compiler can figure out where all the frees go. We don't need frees. Let's get back to our two options. So we said we have these two kinds of memory management. We have unmanaged explicit, like C and C++, where it's up to the programmer to explicitly deallocate objects using free. And we have managed, where objects are automatically reclaimed by a reference counter or a garbage collector. What is Rust? Yeah. Good. Yeah. So it really doesn't fit into either of these the way they're traditionally defined. It's either giving you the best of both or the worst of both, depending on your perspective. It is not requiring explicit free, and it's not doing this at runtime. It is giving you automatically reclaiming storage because the compiler is producing code that reclaims storage when it needs to. So it is automated in the sense that you're not explicitly freeing code, but you're writing code in a way that makes it so you can statically manage memory automatically. It doesn't fit into either of these traditional definitions, and I don't think there's been a really general term established for what it's doing. I think probably the best term would be it's statically managed. The other way to view it is it's explicit in that you do have control of when and where memory is reclaimed. You have control in it by the way you write the code, except for you're not explicitly saying when to free. You have control based on the language rules. So it is explicit in that sense, but it's safe because you don't have the direct control over when an object gets reclaimed. I am just about on time, so we'll have time to make teams for problem set 3. Those of you who can read French can read about the metric prefixes that were introduced in 1991. So your web server should be about 10 to the 42 times better than what you did for problem set 1. If it's only about 10 to the 40 times better, that's still probably good enough.